So in this diagram, we see that the first term has only one sub-diagram, but whereas the second term has two sub-diagrams and the third term has only one diagram. So terms where there are more than one sub-diagrams, they are called disconnect diagrams. And we'll see that when we actually multiply our numerator by the denominator, such disconnected diagrams will go away. So below, we will also deal with how to, we will show how to deal with the denominator, which, let me remind you, where t goes to 1 minus I epsilon infinity, and then this goes 0, the time ordered exponential of minus I, and this goes from minus t to plus t dt hi of t. And what we will see is that when we consider the diagrams which are coming from this denominator, they will cancel terms where in the numerator where we have disconnected diagrams like this. Okay, we haven't proved this, but we'll show it soon enough. So with that in mind, we can draw the second order diagram, the connected diagram that we are, or fully connected diagram that we are going to see. And the second order diagram is going to have two vertices. So these guys are called vertices, the internal points. So this is x1 and x2. And the symmetry factor for this will be a factor of 2 from the first loop, the factor of 2 from the second loop. So the symmetry factor will be 4. And then we're also going to have x1 and x2, and then there will be two internal vertices like so. And here what we see is that there's going to be factorial of 3 ways of interchanging these two loops, and therefore the symmetry factor for this diagram is 6. And then we are also going to have a term of the same order where we'll have these two loops in this way. And here we see that there's going to be a symmetry factor associated with this guy, which will be 2, and then there'll be a symmetry factor associated with this thing, which will be 2. And therefore, the symmetry factor for this will be 4. So these observations allow us to write down expressions for amplitudes by first drawing the diagram in the according to, we basically write the numerator. So here I'm showing what the rules will be for general endpoint function. So for each order in the perturbation expansion, we draw all possible diagrams with n external points and write down the corresponding amplitude by using the following position space rules, which are known as Feynman rules. So we, of course, want to evaluate what these amplitudes are, and to derive these amplitudes, we just follow the following rules. For each propagator, between, say, x and y, we just write down, for each line, we write down the Feynman propagator. So for each vertex, that is each internal point, say Z, so for the phi to the power 4 theory, each vertex will have 4 lines attached to them. For each of these, we attach minus I lambda, and we integrate over d4 of Z. And for each external point, for each external point, we just put the number 1. And then finally, we divide the expression by the symmetry factor of the diagram. So these are the position space Feynman rules. In practice, the momentum space Feynman rules are a little bit more useful and more frequently used, although one should also know the position space Feynman rules. So let's just move on to the momentum space Feynman rules. So in computing scattering amplitudes from particle accelerators, we usually need this momentum space Feynman rules. So to derive the momentum space Feynman rules, let's start with the expression of the Feynman propagator in momentum space, that is the Fourier integral expression. There's a factor of I. So thus we see that, suppose we have an internal vertex, say Z, so where 4 propagators meet, and each of these vertex, suppose, has a momentum flowing. Say this guy has momentum flowing in P1, this has momentum, 4 momentum flowing out P2, this has 4 momentum flowing out, which is P3, and this is P4. Then according to the position space Feynman rule, we should get an integral which involves d4z and an exponential of e to the power I, say p1 minus p2 minus p3 minus p4 times z. So if you do this integral, then what we get is 2 pi to the power 4, and then a 4-dimensional Dirac delta function with p1 minus p2 minus p3 minus p4. Now, we recognize this as nothing but the conservation of 4 momentum, that is the conservation of energy and momentum at the vertex z. So thus we get the result that at each point in the Feynman, in the position space Feynman rules, that each vertex we have to preserve for momentum. So with this observation, let us write down the Feynman rules for the momentum space. So number 1 is that for each propagator, with momentum, say P, so there'll be some diagram like this, where this is P. Of course, now because we're in momentum space, these guys don't have any space-time labels, so we can just represent the propagator just by a line. And then that's going to be given by the kernel of the Feynman propagator, that is the kernel of the Fourier transform. So that's number one. Number two is that for each internal vertex, so these are vertices in momentum space, we have, of course, each of these vertex arises from a position space vertex by this integral. So for each vertex, we write minus I lambda. And for each external point, say where there's a momentum going out like that, we write e to the power minus I px. So then we impose momentum conservation at each vertex, and then for each undetermined momentum, we integrate over the momentum, that is, we associate d4 of k by 2 pi to the power 4. So as an example of a diagram where we have an undetermined momentum, we can take the case where we have a momentum coming in, which is p here, and the same momentum must go out p. But here, the momentum in the internal loop can be anything. It can be because whatever is going in this way is coming back this way. So therefore, the momentum in this loop is not determined. Therefore, for such diagrams, we have to include an integral over d4 of k. And we can look at this as we can derive this, of course, just by taking the Fourier transform of the position space diagram. But we can look at this from a quantum mechanical point of view, because in quantum mechanics, what we know is that if there is an amplitude of something happening in two different ways, we have to sum over these two amplitudes. And here what we are seeing is that there is an amplitude of the particle with momentum p going in such a way that there's an internal particle whose momentum can be any momentum k. And therefore, these are all different possibilities, and therefore we have to add over all these possibilities. And that's where this integral comes from. So that was Feynman rule number 5. And then we have Feynman rule number 6. We have to divide by the symmetry factor of the diagram. This hasn't changed.